Hello everyone. Today I will be going to start with module number 3 in finite element method subject. So the third module is about beams and shafts. Uh, in that the content is boundary conditions, load vector, Hermite safe functions, beam stiffness matrix, and numerical problems on beam. In addition to this, we have torsion of shaft, its finite element formulation, and determination of stress and twist in circular shaft. So, I will first of all start with beams. In the later classes, I will start the shafts. So, uh, to start with, uh, let us have the finite element formulation of uh, So it is the finite element formulation of the beams. So in general, a beam is a structural member. It is a long structural member having a small cross-sectional dimensions, and it supports the transverse loads. So basically, it is a long structural member having small cross-sectional area, and in addition to that, it will going to support the transverse loads. So you all have the knowledge about the basics of beams. That is, different types of beams are simply supported beam, cantilever beams, fixed support beams, and overhanging beams. So these are the four different types of beams, wherein we may have the cantilever beam, simply supported beam, fixed beam, and overhanging beam. So, in addition to that, the different types of supports in beams may be fixed support, roller support, hinge support, etc. So, a fixed support is nothing but its all the degree of freedoms are constrained, and in case of roller support, uh, at that particular point, at that particular node, the beam can have the horizontal displacement, or it can have the rotation at that particular point or node in case of the roller support. Whereas in case of hinged support, uh, the beam is constrained along x and y direction, meaning that it cannot displace along x and y direction, but it can have rotation at that particular point or node. So basically, a fixed beam will have all the constraints. So yeah, nothing but it is having the zero displacement along x, y, and also it is not having any type of rotation at that particular point or node. And whereas in case of the hinged support, the beam can have only rotation at that particular point or node, but it cannot displace along x and y direction. And in case of roller support, the beam can have displacement along x direction, and also it can rotate at that particular point, but it is completely constrained along y direction. So these are the different types of supports. So the different types of loads which can act on beam are basically the beam may have the vertical transverse load or concentrated load, and the beam may also have the uniformly distributed load over its entire length, and beam may have the uniformly varying load, and in addition to that, it may have the moments at some locations. So the different types of loads that can act on beam are point load, UDL, UL, and moments. So these are the basics of beams. That is, different types of beams, different types of supports, and different types of loading conditions for a particular beam. So in case of finite element method, basically we need to have the safe function of a beam and stiffness matrix of beam. In addition to that, we may have the load vector due to uniformly distributed load or uniformly varying load. So these are the things which need to be discussed before going for the numericals related to beams. So let us have, first of all, the safe function of a beam. The difference between bar and beam is that a bar is a one-dimensional element wherein each node is having 1 degree of freedom system, and whereas in case of beam, a beam is also a one-dimensional element, but at each node there are 2 degrees of freedom system. That is, it may have the displacement along x direction, that is vertical deflection or vertical displacement along x direction, and it can also have the rotation at that particular point or node. So each node can either have the vertical displacement, or it may also have the rotation at that particular location. So therefore, a beam is considered to be one dimension, but the thing is, it is having 2 degree of freedom at each particular node. So therefore, Lagrangian safe functions cannot be used in case of beams. We have a separate method of having the safe function for a particular beam. So the safe functions which are used in case of beam are called as Hermite safe functions. And an Hermite safe function, in general, it can consider the vertical deflection or vertical displacement along with the rotation at a particular location of a beam. So therefore, as in general, a beam, a one element beam may have 4 degrees of freedom system altogether. So it is required to consider the Hermite safe function for a particular beam, and the order of that Hermite safe function must be a cubic order safe function model. That is, H is equals to alpha naught plus alpha 1 zeta plus of alpha 2 zeta square plus of alpha 3 zeta cube. So this need to be corrected. It is zeta cube. So where alpha naught, alpha 1, alpha 2 and alpha 3 are the generalized coordinates, and the value of these generalized coordinates need to be determined with the help of the boundary conditions available for a particular beam. So we have the cubic order safe function model, Hermite safe function model, and through which it is possible to have the safe function for each degree of freedom of a particular beam. Now, to have the safe function of B, I have considered a table. For this, I have written here zeta is equals to -1, that corresponds to node 1, and zeta is equals to +1, that corresponds to node 2. The zeta value at node 1 is -1, zeta value at node number 2 is +1. And also here it is considered H1, H1 dash, H2, H2 dash, H3, H3 dash, H4, H4 dash. So dash terms represents the rotation or slope. Dash terms represents the rotation or slope, meaning that H1 is the safe function associated with vertical deflection at particular node number 1. H1 dash is the safe function associated with the rotation degree of freedom along the vertical direction. So in general, it is H1 is the safe function with respect to V1 direction, and H2 is the safe function uh, corresponding to the rotation at node number 1. H3 is the safe function corresponding to the vertical deflection of node number 2, and H4 is the safe function corresponding to the rotation of node number 2. So here you need to understand that this H1 dash, it is just the identification. It is identification whether this vertical deflection V1 is associated with linear displacement or rotation displacement. So we definitely understand this V1, it is a linear displacement. It is not the rotation. Similarly, when you consider the safe function along the rotation at the node number 1, definitely it is not a linear displacement. That is, it is not H2, but it is to be H2 dash because it is a slope or rotation. Similarly, when you check at node number 2, V2 is associated with linear displacement, but it is not associated with the rotation degree of freedom. Similarly, when you consider the rotation at node number 2, definitely it is associated with the rotation or slope at node number 2, but it is not a linear displacement. Accordingly, this tabular table is formed, wherein we have considered corresponding to node 1, the value of zeta is -1, corresponding to node 2, the value of zeta is +1. So at node number 1, the total safe functions are h1 and h2. That is h1 along v1 direction, h2 along this theta 1 direction, that is rotation at node number 1, or it is h1 dash. So at node number 1, that is at zeta is equals to -1, the value of safe function at its own node is unity. So h1 will be equals to 1, but it is not a slope, therefore h1 dash will be equals to 0. And when you see at node number 1, h2 is not is equals to 0, is equals to 0 because it is not a linear displacement. This rotation is not a linear displacement, but it is a slope. Therefore, h2 dash is equals to 1. And we do not have the value of h3 and h4 at node number 1, that is at zeta is equals to -1. So the remaining values are equals to 0. Similarly, when you come to node number 2, it is associated with only h3 and h4. So h1 and h2 terms are equals to 0. The value of zeta at node number 2 is +1. For this, h3 is equals to 1. That is, the value of safe function at its own node is equals to 1. So h3 is 1, but it is not a rotation, therefore it is 0. And h4 is 0 because it is a rotation, it is not a linear displacement. And h4 dash is obviously equals to 1 because it is a rotation degree of freedom system. So it is required to form this table before going for the derivation of the safe function. So corresponding to the vertical deflection, the safe function is h1. Corresponding to the rotation, the safe function is h2. Corresponding to vertical deflection at node number 2, h3. And corresponding to the rotation of node number 2, the safe function is h4. So to derive h1, let us consider the safe function model first. H1 is equals to alpha naught plus alpha 1 zeta plus alpha 2 zeta square plus alpha 3 zeta cube. And differentiating this h1 with respect to zeta. So we get alpha 1 plus 2 alpha 2 zeta plus 3 alpha 3 zeta square. Now we have to determine the value of generalized coordinates alpha naught, alpha 1, alpha 2 and alpha 3 with the help of boundary conditions. Now when you look at node number 1, the value of h1 from this table at node number 1, meaning that it is at zeta is equals to -1, h1 value is 1. So here I have written h1 is 1, zeta value is -1, and h1 dash at node number 1 is equals to 0. So therefore, when I use these boundary conditions in these two equations, we will get 1 is equals to alpha naught minus of alpha 1 plus of alpha 2 minus of alpha 3. Similarly, when you use the boundary condition in the second equation, we will get 0 is equals to alpha 1 minus of 2 alpha 2 plus of 3 alpha 3. So at node number 2, h1 value is 0, zeta value is +1, h1 dash is 0. So substituting these boundary conditions, we will get 0 is equals to alpha naught plus alpha 1 plus alpha 2 plus alpha 3. And when you substitute in h1 dash equation, you will get 0 is equals to alpha 1 plus 2 alpha 2 plus 3 alpha 3. So adding these equations, that is equation 1 and 3, that is equation 2.8.4a and 2.8.4c, so we'll get this. And adding these two equations, that is 1 and 3, so we'll get this. Similarly, adding the b and d equations, we'll get this. So simplifying, we'll get the value of alpha naught, alpha 1, alpha 2 and alpha 3. So wherein we'll get alpha naught as 1 by 2, alpha 1 as -3 by 4, alpha 2 as 0 and alpha 3 as 1 by 4 with this simplification. So you can see the equation one more time. So wherein we have to add 1 and 3 and 2 and 4 and subtract 1 and 3 and 2 and 4. With this method, it is possible to get the value of alpha naught, alpha 1, alpha 2 and alpha 3. So these are the values, and once you get those, you can substitute the value of alpha naught, alpha 1, alpha 2, alpha 3 in the assumed safe function model of h1. We will get an equation which is the safe function corresponding to node 1 displacement, linear displacement equation, which is equals to 1 by 4, 2 minus of 3 zeta plus of zeta cube. Similarly, you can consider the same cubic order displacement function, safe function model for determining h2. Again, you have to consider H2. You have to differentiate H2 with respect to zeta. You have to consider the boundary conditions of H2, H2 dash at node number 1 and at node number 2. And you have to have the four equations corresponding to node 1 and node 2. Then you have to add equation 1 and 3, equation 2 and 4, subtract equation 1 minus of equation 3, subtract equation 2 minus of equation 4. Then you will get the value of alpha naught, alpha 1, alpha 2, and alpha 3. So you will get these values. When you substitute in an H2 equation, you will get H2 is equals to 1 by 4, 1 minus zeta, minus of zeta square plus of zeta cube. Similarly, in a similar way, you can have the equation for H3 as well as equation for H4. So ultimately, the Hermite safe function model, safe functions are H1, H2, H3, H4. And when you write the definition of safe function here, that is the field variable is equals to the nodal variable into the safe function. So field variable here we are writing in terms of V of zeta, which is equals to H1 V1 plus of H2 V2 plus of H3 V3 plus of H4 V4. But the thing here is the H2 and H4 are associated with slopes. So therefore, instead of V2 and V4, it is written dou V by dou zeta with respect to node 1, dou V by dou zeta with respect to node 2. So, in other words, the field variable, all of you have to understand, field variable in case of beam can be written as H1 LE by 2 H2, H3 LE by 2 H4 multiplied with the corresponding displacements V1, theta 1, V2, theta 2. V1, V2 are the vertical deflections corresponding to node 1 and 2. Theta 1 and theta 2 are the rotations at node number 1 and 2. So in general, we can write field variable V is equals to H into Q, where H is the safe function values of corresponding to H1, H2, H3, H4. The only thing, H1 it is considered as it is. H2 is to be multiplied with LE by 2 because it is a slope, and H4 also need to be multiplied with LE by 2 because it is also a slope. So in addition to this, we can have the variation of safe function model, variation of safe function models. So this is the figure corresponding to the variation of H1, variation of the H1. This is the figure corresponding to variation of H2. This is the variation of H3, and this is the variation of H4. So all of you note these things. So first of all, the safe functions are H1, H2, H3, H4, corresponding to the 4-degree freedom problem of the B. And the field variable in general, it can be written as V is equals to H into Q, where H is the matrix of the safe function, H1, H2, H3, H4. H2 and H4 are multiplied with LE by 2 because they are associated with slopes, and Q is the deflection or nodal displacement vector. So nodally, it is consisting of V1 theta 1 and V2 theta 2. So therefore, these are the H value, and these are the variations of the safe function of the V. Thank you for listening the video.